Welcome to the Math 1 lesson summary video for the task Up a Little, Down a Little. Summary, this is a solidify understanding task. So some of the things we've been learning in this module, we're putting them into action more efficiently and effectively, hopefully, and we're starting to feel solid about our understanding. So Mama Big Bucks here has put $20,000 into a bank savings account that pays 3% interest compounded annually. Compounded annually means that at the end of the first year, the bank pays Mama 3% of the $20,000, so they add $600 to the account. So we have $20,000 multiplied times 0.03, which is 3% as a decimal, and that's $600. So they're adding that to the $20,000 to get $2,600, and they're going to multiply that at the end of the second year times 0.03 to figure out what amount gets added to the $2,600, and so on and so forth. So as we've talked about, a faster way of doing this than multiplying this and then adding it to 20,000 is to just multiply by 1.03. So to model the amount of money in Mama Big Buck's bank account after T years, I might use a recursive rule. So in this case, I'm going to use T for years because they asked me to. So f of T, or f sub T equals f sub T minus 1 times 1.03. F sub 0 equals 20,000. But to answer question B, it says use your model to find the amount of money that Mama has in her account after 20 years. That's going to take quite a long time. So it's probably helpful for me to create an explicit rule. F of T. So as we've learned with geometric sequences and as a result exponential functions, which is what this is an exponential function, we have the starting amount, so 20,000, multiplied by the common ratio, 1.03, raised to the power of T. And so to find the amount of money that Mama has in her account after 20 years, we're just finding f of 20. So 20,000 times 1.03 to the 20th power, and that comes out to be $36,122.22. So that's a pretty good return on investment for her. All right, so question 2, it says when the value of something you buy goes down by a certain percent each year, it's called depreciation. For example, Mama Big Bucks buys a car for $20,000 and it depreciates at a rate of 3% per year. So this time, when we take the 20,000 and multiply it by 0.03, it's still 600, but we're doing 20,000 minus 600 instead of plus 600 to get the 19,400 that the value of the truck is going to be at the end of the year. And so as we talked about, if it loses 3% of its value, that means it keeps 97% of its value. So an easier way to do this, instead of multiplying and then subtracting, is to just multiply by 0.97. So f of t equals f of t minus 1 times 0.97. F sub 0 equals 20,000. So again, we want to write an explicit rule. So using what we've learned about geometric sequences and exponential functions, we have our starting amount multiplied by the common ratio raised to the power of t. So now we have a different question this time. It says use your model to find how many years it will take for Mama's car to be worth less than $500. So to do that, I'm going to want to graph this equation in Desmos. So as I've mentioned with Desmos, instead of using t and f of t, I like to just use y and x. So we have y equals 20,000 times 0.97 raised to the x power. And the reason I do that is so that when I duplicate it and convert it to a table, it all comes out nicely. So negative values don't make sense in this context for the domain. So our question is, when is it going to get down to $500? And so we can just keep on trucking, pun intended, until we get down to $500. And so you can see this is a nice, efficient an easy method to use is by making the technology table, and you could do the same kind of thing in your calculator, but all different schools use different calculators, but everyone has access to Desmos, so that's why I've chosen to use Desmos. So it's going to be sometime between 45 and 46 years. So we'll say approximately 46 years to answer that question. And so just want to take a quick sec to compare this graph. So I've created a nice window where we can view the graph. And so we can see that's what it's looking like for the depreciation scenario. And since we've already gotten the answer we want from this table, I'm going to take that out. And so let's compare that to the bank account where it was appreciating, where we had the 1.03 to the x power. So you can see there's a relationship between these two. The one is increasing exponentially, the other is decreasing exponentially. And so the graphs are kind of reflections of each other over the y-axis, which is just interesting. And you can see they have the same y-intercept. So what you notice is we had different situations that were based on a percent rate. So we want to break down this formula, f of t equals a times 1 plus or minus r to the t power. So in both cases with Mama Big Bucks, a was 20,000. And in both cases, r was 0.03, which is the decimal representation of 3%. So in the one formula, when it was appreciating, you can see how we did 20,000 times 1 plus 0.03 to the t power. And that's where we got the 1.03 from. So that was for the appreciation in problem 1. For the depreciation in problem 2, we still did 20,000, but it was times 1 minus 0.03 to the t power. And that's how we got 0.97. So this formula is a way of summarizing that process in a more formulaic way if you prefer. Thanks for watching. And if you need help with the Ready, Set, Go problem specifically, please check out the Ready, Set, Go support videos in the student support site in Canvas.